Now we're going to discuss how rotation is going to affect energy of a system. So let's go back to our bicycle wheel example. Imagine our bicycle wheel is rotating, so let's let it spin around like this. So spinning around like that, and let's say it spins with some sort of, an angular speed omega. So it goes around omega radians per second. Now, as it spins, even if the wheel is stationary, so imagine you pick up the back of your bicycle and you turn the pedals and make the wheel turn around. So as the wheel rotates, you have all these little bits of mass that make up your wheel. They're all moving. Even though the wheel as a whole is not moving, all these little bits are moving. That means that all these little bits, all these molecules, they all have some kinetic energy associated with this rotational motion. So now we have a rotational kinetic energy. So K rotational, or K ROT, or I'll start using K sub R for rotational kinetic energy. The rotational kinetic energy is 1/2 replace the mass with the moment of inertia, and replace the speed with the angular speed. So 1/2 I omega squared. This is the rotational kinetic energy of this wheel. Now, the wheel can also be moving along the ground. So let's say the wheel is on the ground and the bicycle is rolling across the ground. So the wheel's rotating while the bicycle and the wheel are moving. That gives us not only rotational kinetic energy, but what we call translational kinetic energy. And I'll just use a subscript T for the translational kinetic energy. And this is 1/2 the mass of the thing times the center of mass speed squared. So imagine we have our bicycle wheel. Let's draw the ground here, and let's draw a bicycle wheel. Here's our wheel, and let's say we let the wheel rotate around like this, but at the same time it's moving forward. So what we have here is a total kinetic energy, which is equal to the rotational kinetic energy plus the translational kinetic energy. So what we have to do now is we split the kinetic energy into two parts. One part for rotational, that's 1/2 I omega squared plus 1/2 its mass times its center of mass speed squared. So this, translational, that's how the object moves through space. Rotational is just it spinning or rotating around. Something we can do with the rotational kinetic energy is think about what's going to give rotational kinetic energy. A force would give translational kinetic energy. A torque would give rotational kinetic energy. So we can rewrite the work energy theorem, this time for rotation. Remember, before it was the work is equal to the change in kinetic energy. Well, that's still true, but this would be the work done by a torque. So we say that the work done by a torque is equal to the change in our rotational kinetic energy, which would be 1/2 moment of inertia times your final angular speed squared minus 1/2 I times your initial angular speed squared. This is the work that's done by a torque. This is our work energy theorem for rotational motion. Now we look at the special case of rolling without slipping. So we have something rolling across a surface, but there is no slippage between the surface of the object and the surface of the ground or the floor or whatever it is. So we have two sorts of motion that are kind of combined here. We have our translational motion that looks like this, so the whole thing moving in a certain direction, plus we have this rotational motion that's going on while it's spinning or rolling along. When you combine these two together, we can see what's happening at different points along the edge of the object. So at the bottom, see as it rotates, there is a very important relationship. At the edge, the tangential speed at the edge, if it's rolling without slipping, only if it's rolling without slipping, that tangential speed is going to be equal to the speed of the center of mass. Not the velocity of the center of mass, but the speeds will be the same, because the direction depends on where you are around the circumference of this object. So, as it rolls without slipping, you see on the bottom, this little molecule, or this bit right here, is moving backward due to the rotation, but because the motion of the center of mass is moving forward. Those two speeds are the same, so they cancel. So as something hits the ground here, as it rolls around, like on your tires of your car, as that part of your tire hits the ground, that piece of tire on the ground is momentarily at rest. So when it hits the ground, it's at rest. That's why we have static friction between your tire and the road, because it is momentarily at rest relative to the surface of the ground or the road. And as you go up, you see you can add these two vectors together here. This one's pointing up, this one's pointing that way, so the velocity of that piece would be up and to the right. Up here, the piece at the very top has twice the speed because these two would combine. And then here you see add the vectors again, same thing. The biggest thing to remember here is this statement. This is extremely important because we're going to be using energy conservation with things that are rolling without slipping. It's important that we're able to make this connection. So what is Vtan? Vtan is the angular speed times this distance, r. So this is the relationship that we have to be able to make. Another relationship, you can do this for all the angular quantities, if it's rolling without slipping. Another one that's very important to make is the displacement. So if this thing rolls across the ground, whatever distance that it rolls, so let's say it rolls in the positive x direction, and I'm just using positive x arbitrarily. It could be y, could be z, could be whatever. So let's say it rolls in the x direction. So there's an x displacement. Well, that x displacement for the center of mass of this thing would be equal to the arc length, which would be r times the angular displacement. So the linear displacement is equal to the arc length, which is r times the angular displacement. This is another really important thing to keep in mind. Acceleration, same thing. we say that if it's rolling without slipping, the tangential acceleration at the edge of the thing is going to be equal to the center of mass acceleration, which means atan, that is r times the angular acceleration, has to be equal to that center of mass acceleration. These connections are very important for you to make, otherwise you won't be able to solve these problems where you have rolling without slipping. Now I mentioned that we'd be talking about conservation of energy. So we know about the kinetic energy. This is important because what we can do, I'll talk about this when we get to the conservation of energy thing in just a second, but what we can do is you can write the tangential and rotational ones in terms of each other. But we also have a gravitational potential energy that we need to worry about. So where on this thing is the position that we use for, remember, gravitational potential energy was mg times y. What position y do we use? If this thing is sitting on top of a hill, what do we use for y? Because it takes up some space, so there are all kinds of different values for y that we could use. Well, since gravitation is going to act at the center of mass, then we use the center of mass position. So it's a center of mass coordinate, y coordinate, that matters for the gravitational potential energy. So this is what we'd use for gravitational potential energy for an extended object. Now we can include all these things together to get one conservation of energy equation. And this is what that's going to look like. We have potential energy, we talked about that right here, plus kinetic energy. Include both energies here. So translational plus rotational, and that's going to be constant. And remember, you can pick different points in time to measure these. So what do we put here? We put mg y center of mass plus translational kinetic energy, 1/2 m times v center of mass squared plus rotational kinetic energy, 1/2 I omega squared. Again, that's equal to a constant. I'm just going to use a capital C for constant. This is a constant value. Now, we can use this and either plug this in for v center of mass, so you get omega squared r squared, or you can use this and plug v squared over r squared in place of omega squared.